Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this big circle, and in the second question, we'll find out the area of this rectangle ABCD in two different methods. So we'll start with the first question. In the drawing, we have two circles that touch each other at point C, or those two circles are tangent to each other at point C. In addition, we know that line segment AC equals to 60 units in its length. This is line segment CB, that is equal to 9 units in its length. And this is tangent DE, that is tangent to this small circle at this point B. In addition, tangent DE is tangent to this big circle at this point. We define the point of tendency of tangent DE with this big circle. This point is point M. Repeat again that our mission is to find out the area of this big circle. So, we'll focus at this point, on this point B. Point B is considered as an external point in relation to this big circle. So from this common external point B, we have tangent BM, that is tangent to this big circle at point M, and from the same common external point B, if we draw the straight line BC and extend it, it will cut the big circle at 2 points, point C and A. In this way, we created chord CA. So from the same common external point B, we have tangent BM, and also we have here chord CA. So actually, we can implement here rule 10. So we will click on rule 10. According to rule 10 is true in any circle. In any circle, if AB is any chord in the circle, here AB is a chord in this circle, and PT is a tangent to the circle. PT is a tangent to this circle at point T. So from the same common external point B, if we extend, if we draw a straight line and extend the straight line, and we get chord AB, and from the same common external point B, we have tangent PT that is tangent to this circle at point T. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So according to rule 10, if you have a common external point, and from a common external point you will draw a tangent, and from the same common external point you will draw a straight line until it crosses the circle at 2 points, and it will create a chord. Then in this drawing, the following equation will be true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, from the common external point B, we have tangent BM to this big circle, and from the same common external point B, if we do this straight line and extend the straight line, it will cut the circle at 2 points C and A. In this way, we create chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation will be true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I'll write it down. So according to rule 10, BM squared equals to BC times BA. Repeat again. According to rule 10, if you focus on this common extent point B, the following equation will be true. That BM squared equals to BC times BA. BM is the missing tangent, so we leave it as it is. So it is BM squared, and it is equal to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So in total, according to rule 10, we actually found out that BM squared equals to 9 times 25. Here we take root out of this equation, and we get that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So we found out that the length of tangent BM is equal to 15 units. Okay, BM, this is tangent BM, and it is equal to 15 units in its length. In the next step, we will do a construction. That is to say, from point C, we will draw a common tangent. A common tangent is a tangent that belongs to both circles, to the big circle and to the small circle. So we draw a common tangent, and we extend the common tangent until it touches tangent DE. And we define the touching point of the common tangent with tangent DE. This point is point N. I repeat again that the common tangent CN is tangent to the small circle at point C, and the common tangent CN is also tangent to the big circle at the same point C. Okay. So, in the next step, we will focus on this common example point N. From this common example point N, we have two tangents to the small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. This is to say, NC equals to NB. So, I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common example point to a circle are equal. In the drawing, we have a circle. This is the common example point P. From this common example point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. As I already mentioned before, we can definitely implement rule 2 in our drawing. Well, if we focus on the common example point N, from the common example point N, we have two tangents to the small circle, tangent NC and tangent NB, and according to rule 2, they are equal to each other. That is to say, NC equals to NB. In the next step, I will join points M and C together by stripe 9. Point M is the point of tendency of tangent DE with this big circle. So in the next step, I will copy triangle CNB, this triangle CNB, in a new page, and we will analyze this triangle CNB. So actually, this is triangle CNB, this is a copy from the original drawing. According to rule 2, side CN equals to side NB. And we have the rule that states that in the front of equal sides in the triangle there are equal angles. In front of this side NB we have this angle, that is angle NCB. In front of this side NC we have this angle, this is the angle CBN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So if we found out that angle NCB equals to alpha, this is angle NCB that is equal to alpha, and also angle CBN also equals to alpha. Angle CBN equals to alpha. We will continue to focus on this common standpoint, point N. From this common standpoint, point N, we have two tangents to the big circle, tangent NM and tangent NC. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. NC equals to NM. So, in the next step, I will copy triangle CMN in a new page, and we will analyze this triangle CNM. So actually this is triangle CNM that I copied from the original drawing. According to rule 2, side CN equals to side NM, and according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle, that is actually angle CMN, and in front of this side NM we have this angle, that is actually angle NCM. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, according to the rule that I mentioned. So in total, if we found out that angle MCN equals to beta, this is angle MCN that is equal to beta, and angle CMN also equals to beta. Angle CMN equals to beta. In the next step, I'll copy the big triangle CMB in a new page and analyze this big triangle CMB. So actually, this is triangle CMN that I copied from the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees. Therefore, the sum of the angles in this triangle CMB must be equal to 180 degrees. So which angles we have in this triangle CMB? We have this angle that is alpha, plus this angle that is beta, plus this third angle that is beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta, and it is equal to 180 degrees. So 2 alpha plus 2 beta equals to 180 degrees. Here we divide this equation by 2, and we get that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So alpha plus beta equals to 90 degrees. That is to say, angle MCB, that is equal to alpha plus beta, it is a right angle. So actually, this is angle MCB, and this angle MCB is a right angle. Okay. We know that AB is a straight line. We also know that AB is a straight line, and the length of the straight line AB is 16 plus 9, that is 25. Anyway, AB is a straight line. So if we focus on the left side of this straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AB at point C? We have this angle that is the right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So we found out that angle ACM is the right angle. This is angle ACM, that is the right angle according to rule 3. In the next step, we join points A and M together by a straight line. And we relate to the big circle. So inside this big circle, we have peripheral angle ACM. This is peripheral angle ACM, and the size of this peripheral angle ACM is 90 degrees. It is a right angle. And peripheral angle ACM subtend on chord AM. Again, peripheral angle ACM, that is a right angle subtend on chord AM. Here we can implement rule 5. So I'll repeat quickly on rule 5. According to rule 5 is true in any circle, of course. Any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So here normally we have a circle, and this is peripheral angle MAN, and we know that peripheral angle MAN is a right angle. Again, peripheral angle MAN is a right angle, and therefore any peripheral angle that is equal to 90 degrees in its side must subtend on the diameter of the circle. And because of the fact that peripheral angle MAN that is equal to 90 degrees inside subtend on MN must be the diameter of this circle according to this rule, rule 5. We can definitely implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle ACM, that is a right angle, and according to rule 5, any peripheral angle that is a right angle must stress on the diameter, must subtend on the diameter of the circle. Here, peripheral angle ACM, that is a right angle, subtend on AM, and therefore AM must be the diameter of this circle, the big circle, according to rule 5. So I write it down. Chord AM is the diameter of the big circle according to rule 5. Okay. We also know that the center of the circle is located on the diameter of the circle. Again, the center of a circle is located on the diameter of the circle. Therefore, the center of this big circle must be located on AM, that is the diameter of this circle, according to rule 5. So, this is the center of the big circle that is definitely located on the diameter AM. We define the center of the circle as O. So point O is the center of the big circle, point M is the point of the big circle itself, therefore OM is the radius of this big circle. We define the radius of the big circle as R, therefore OM equals to R, according to our definition. And because of the fact that the radius OM that is equals to R, the radius OM of the big circle that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1, of course. Okay, so in the next step, I'll copy the right big triangle A and B. In the new page, we'll implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. MB, side MB of the right triangle A and B equals to 15 units according to rule 10. AM is the missing side, and the hypotenuse AB in total equals to 16 plus 9, that is 25. So actually, this is the right triangle A and B that according to the original drawing, according to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. So I'll write it down. So AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. The hypotenuse AB is 25, therefore AB squared is 25 squared, that is 625. And it is equal to AM squared. AM is the missing side, so we leave it as it is. So it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, we found out that according to the Pythagoras theorem, this right triangle A and B, 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we'll get that 625 plus 225 is 400, so 400 equals to AM squared. So here we take a root out of this equation, and we get that AM That is the diameter of the big circle is equal to the square root of 400, that is 20. So the diameter of this big circle, the diameter AM equals to 20 units in its length. We know that the radius of any circle is half of the diameter. So the radius R of this circle must be equal to the diameter AM over 2. The diameter AM equals to 20, so 20 over 2 is the length of the radius of the circle, so 20 over 2 is 10. So in total we found out that the radius of the big circle R equals to 10 units in its length. Our mission is to find out the area of this big circle. We actually know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again. The area of any circle is equal to pi times the radius of the circle squared, and therefore the area of our circle, the area of the big circle, must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. So in total we found out that the area that we are looking for this question, that is the area of the big circle, equals to pi times 10 squared. So it is pi times 10 squared. 10 squared is 100. So in total we found out that the area of the big circle equals to either 100 pi square units, so in terms of numbers, it is equal to 314.159 square units. And that is the answer to the first question. Repeat again. We actually found out that the area of this big circle equals to either 100 pi square units, so in terms of numbers, it is equal to 314.159 square units. We finished with the first question. In the next step, I'll present to you the second question, and we'll solve the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. And we find out the area of this rectangle ABCD in two different methods. So we start with the first method. In the drawing we have rectangle ABCD, and we have also this semicircle. In addition, we know that this is 9/7 AM, that is equal to 5 units in its length. And our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is rectangle, all those four angles inside rectangle ABCD are right angles. So here, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. The next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. So point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x units in its length according to our definition. In the next step, we define the point of tendency of tangent DC with this semicircle. This point is point E. In the next step, we join points O and E together by a straight line. What is the definition of line segment OE? It starts from point O, that is the center of the semicircle, and ends at point E, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle, that is equal to x units in its length according to our definition. OE is the radius of the semicircle. In the next step, we join points O and N together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is equal to x. We define the length of this line segment OB as A, and we define the length of this line segment MB as B. So in the next step, I copy the right triangle MOB in the new page, and we implement the Pythagoras theorem in this right triangle OMB. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle NBO that according from the original drawing, according to the Pythagoras theorem, in this right triangle NBO, MO squared, that is the square of the hypotenuse, equals to MB squared plus BO squared. So I write it down. MO squared, that is the square of the hypotenuse, is equal to MB squared plus OB squared. The hypotenuse MO is x, therefore MO squared is x squared, and it is equal to MB squared. MB is B, therefore MB squared is B squared, plus OB squared. OB is A, therefore OB squared is A squared. So in total, according to equation 1, actually found out that x squared equals to b squared plus a squared. In the next step, I'll copy the right big triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right triangle A and B. The length of side AB of the right triangle A and B equals in total to x plus a. The length of side A and B is B, and the length of the hypotenuse AM is 5 units, according to what is given us in the question. So actually, this is the right triangle A and B that according to the original drawing. According to the Pythagoras theorem, in this right triangle A and B, MA squared, that is the square of the hypotenuse, equals to MB squared plus BA squared. Then MA squared equals to MB squared plus BA squared. So I'll write it down. MA squared, that is the square of the hypotenuse, equals to MB squared plus AB squared. The hypotenuse MA is 5, therefore MA squared is 5 squared, that is 25, and it is equal to MB squared. MB is B, therefore MB squared is B squared plus AB squared. AB is x plus A, therefore AB squared is x plus A squared. So today we found out that 25 equals to B squared plus x plus A squared. So 25 equals to B squared plus x plus A squared. X plus A squared equals to x squared plus A squared plus 2 times x times A. This is equation 2. So actually, in the right side of the equation 2 we have the expression B squared plus A squared. But we already found out that according to equation 1, B squared plus A squared equals to x squared. So we can substitute b squared plus a squared in this equation 2, by x squared from equation 1. We'll do it now and we get that according to equation 2, 25 equals to b squared plus a squared is x squared, plus x squared again, plus 2xa. So in total we found out that according to equation 2, 25 equals to x squared plus x squared is 2x squared plus 2xa. So again, according to equation 2, we found out that 25 equals to 2x squared plus 2xa. Here we divide this equation 2 by 2, and we get that 25 over 2 is 12.5. And it is equal to 2x squared over 2 is x squared. 2xa over 2 is xa. So in total, according to equation 2, we should find out that 12.5 equals to x squared plus xa. So 12.5 equals to, here we take out s a common factor from those two expressions. So x was taken out as a common factor. What is left from x squared after we took from it x as a common factor? What is left? It is actually x. And what is left from the expression xa after we took from it x as a common factor? What is left? It is actually a. So in total, according to equation 2, we actually found out that 12.5 equals to x times xa. Again, 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. The area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of a rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB times the width. The width is DA. We have already found out in the first method that dA equals to x. So I'll not repeat on the same process. We have already found out that dA equals to x in the first method. Therefore, we can write it down. dA equals to x units in its length according to the first method. So in total, the area of rectangle ABCD must be equal to the length AB times the width DA. The length AB in total equals to x plus a. and the width dA is x. So in total we have found out that the area that we're looking for this question, that is the area of rectangle ABCD, it is equal to x plus a times x. But according to equation 2, x plus a times x is 12.5, therefore we can substitute x plus a plus x by 12.5 according to equation 2. So in total we have found out that the area of rectangle ABCD equals to 12.5 square units. And that is the answer to the question. Repeat again, the area of this rectangle ABCD is equal to 12.5 square units. We finish with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. Actually, in the first method, I have to prove that AD equals to x, and here it is very simple to prove that AD equals to x. Why? Because of the fact that the radius OE of this semicircle is drawn to point E. That is the point of tendency of tangent DC with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO according to rule 1. If D is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral ADEO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DE OA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least rectangle not a square. So we write to quadrilateral DEOA is rectangle because it has 4 right angles. So quadrilateral DEOA is rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But because of the fact that EO is the radius of the circle that is equal to x, therefore the opposite side DA must be also equal to x units in its length. Okay? In this way we proved that DA equals to x units. Okay, now in the second method, I will not repeat on the same process. We have already proved in the first method that dA equals to x. Okay. So in the next step, we'll prove that rectangle ABCD and the area of we found out the area of rectangle ABCD in the second method. So because of the fact that ABCD is rectangle, all those 4 angles inside rectangle ABCD are right angles. Okay. This is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle, this point O. We define the radius of this semicircle, x, exactly as we did in the first method. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that is equal to x unit in its length according to our definition. As I already mentioned before, we only found out that sine dA equals to x in the first method, so I'll not repeat on the same process. We have to build here a rectangle, and you know that the opposite sides of rectangle are equal to each other, and we derive that dA equals to x. Okay, dA equals to x according to the first method. In the next step, we define this line segment OB as A. We define this point as N, and we join points M and N together by a straight line. By doing this construction, we created a peripheral AMN. This is peripheral AMN that subtend on AN, that is the diameter of the semicircle, and according to rule 7, any peripheral angle that subtend on the diameter of the semicircle or circle must be equal to 90 degrees in its size. So I'm going to quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. So, in the drawing we have a circle, and we know that AB is the diameter of the circle. Again, we know that AB is the diameter of the circle, and we also know that peripheral angle ACB subtend on AEB, that is the diameter of the circle. And because of the fact that peripheral angle ACB subtends on the diameter of the circle, it must be equal to 90 degrees in its size. So this peripheral angle ACB is a right angle. Any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. We can definitely implement rule 7 in our drawing. Why? Because of the fact that peripheral angle AMN subtend on AN, that is the diameter of the semicircle, peripheral angle MAN must be equal to 90 degrees in its size according to rule 7. So peripheral angle MAN is a right angle. In the next step, we define this angle as alpha, and we focus on the right angle AMN. On the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we'll focus on this right angle A and B. On this right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. To the same logic, because 90 degrees minus 1 plus 1 is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. If angle A, this is angle A, that is a common angle, it belongs to both triangles. Angle A belongs to triangle AMN, and this angle A also belongs to triangle AMB. So in the next step, we'll copy the two right triangles, triangle AMN and triangle AMB, in the new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. The diameter AN is twice as big, is twice as long as the radius, that is x. So the diameter, if the radius is x, the diameter AN must be equal to 2x. AM equals to 5 units in its length. A being total equals to A being total equals to x plus A. So actually, those are the two right triangles AMN and AMB that are come from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is again AMN. and it is equal to this angle. It is a triangle ABM in the right angle AMB. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle A and this is angle A. It is the same angle that belongs to both triangles. So we can write down that angle A equals to itself. It's a common angle that belongs to both triangles. So if we relate to angle A as it belongs to the right angle AMN, it will be defined as angle MAN. And angle A equals to itself. So if we relate to angle A as it belongs to this triangle A and B, it will be defined as angle MAB. This equation means that angle A equals to itself. We just called to angle A two different times. So angle A equals to itself is a common angle that belongs to both triangles. You can see here, angle A belongs to both triangles. And finally, those two angles are both equal to 90 degrees from somewhere, therefore they are equal to each other. So here this is again MNA. In the right triangle AMN, and it is equal to this angle, that is actually angle AMB, in the right triangle AMB. They are both equal to 90 degrees from alpha, therefore they are equal to each other. So we will prove that all the triangles of this right triangle AMN are correspondingly equal to all the triangles of this right triangle AMB, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those, so I write it down. So triangle AMN, this is triangle AMN, and this is similar, this is the sign of similar to the right triangle AMB, according so angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of the right triangle AMB over side AN of the right triangle AMN is equal to side AB of the right triangle AMB over side AM of the right triangle AMN. So repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM is 5 is the diameter of the semicircle, that is 2x, and it is equal to AB. AB is x plus a, over AM. AM is 5. So in total, according to equation 1, we should find out that 5 over 2x equals to x plus a over 5. Here we cross multiply this equation, equation 1, and finally get that according to equation 1, 5 times 5 is 25, equals to 2x times x plus a. And again, according to equation 1, we actually found out that 25 equals to 2x times x plus a. In the next step, we divide this equation 1 by 2. And you get that according to equation 1, 25 over 2 is 12.5, and it is equal to 2x over 2 is x, so in total this expression equals to x times x plus a. So in total, according to equation 1, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. Repeat again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABC times the width. What is the length of this rectangle ABCD? The length is AB. So the length is AB, and the width is DA. So in total, we found out that the area that we are looking for this question, that is the area of rectangle ABCD, equals to AB times DA. AB is x plus a, and DA is x. So in total, we found out that the area of rectangle ABCD equals to x plus a times x. But according to equation 1, x plus a times x is 12.5. Therefore, we can substitute x plus a times x by 12.5 from this equation 1. We'll do it now. We get that in total, the area of rectangle ABCD is equal to 12.5 square units. Repeat again, Repeat again. In both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square meters. Okay, so in the next step, I will summarize the lecture. We start with the first question. Our mission in the first question is to find out the area of this big circle. So in the drawing we have two circles that are tangent to each other at this point C. In addition, we know that this is line 7CB, that is equal to 9 units. This is line 7CA or chord CA, that is equal to 6 units in its length. This is tangent DE, that is tangent to this small circle is point B, and tangent DE also tangent to this big circle and this point M. Again, our mission is to find out the area of this big circle. So first of all, we define the point of tendency of tangent DE with this big circle. This point is point M. And we focus on this common external point B. Point B is an external point in relation to this big circle. So from this common external point B, we have tangent BM to the big circle, and from the same common external point B, if we do this straight line, it will cut the big circle at 2 points, A and C. In this way, we create chord AC. So actually, all the requirements of rule 10 are satisfied, and therefore we can implement a rule 10. According to rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So repeat again. According to, if we focus on point B, according to rule 10, BM square equals to BC times BA. BM is the missing side, so it is BC is 9, BA in total equals to BC times CA. That is to say it is 9 plus 16, that is 25. So BC in total equals to 25. So if we found out that BM square equals to 9 times 25, we have to go to all of this equation, and we found out that AM, that BM, this is tangent BM, it is equal to the square root of 9, that is 3, times square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So the length of this tangent BM is 15 units. Okay. In the next step, we did a construction. That is to say, from the point of tendency of those two circles, that is actually point C, we do two common tangents to those two circles, and we defined the touching point of the common tangent with tangent DE. This point is point N. Actually, CN is a common tangent that belongs to both circles. Why? Because CN is a tangent to this small circle at point C, and CN also tangent to this big circle at the same point C. So CN is a common tangent that belongs to both circles. So, and again, we define the touching point of the extended tangent, common tangent, with tangent DE. This point is point N. So from this common point N, we have two tangents to this small circle, tangent AB and tangent NC. And according to rule 2, they are equal to each other. That is to say, C equals to NB. In the next step, a copy triangle CNB. In the page, analyze this triangle CNB. Okay. This is triangle CNB. This is according to the original drawing. In this triangle CNB, side CN equals to side NB according to rule 2. In front of this side NB we have this angle, in front of this side CN we have this angle. So those angles are located in front of those two equal sides, and therefore they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles. Okay? So if we found out that those two angles are both equal to alpha. In the next step we join point C and M together by a straight line. And we continue to focus on this connection point M. For this connection point M, and we have two tangents to this big circle, tangent NM and tangent NC. And according to rule 2 they are equal to each other. That is to say, NC equals to NB. In the next step I copy the right triangle C and M in a new page and analyze this right triangle C and M. So this is triangle C and M, this is according to the original drawing. According to rule 2, Cn equals to Nm. So according to the sum rule, that states that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those angles, and therefore those two angles must be also equal to each other in their sizes. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So in total, if you found out that those two angles are both equal to beta. In the next step, I copied the right triangle CMB. It is not right triangle, it is not right triangle. I call it triangle CMB in a new page and analyze this triangle CMB. Actually, this is triangle CMB, this is according to the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in this triangle CMB must be equal to 180 degrees. So which angles we have in this triangle CMB? We have, this is angle alpha plus angle beta plus angle beta plus alpha. In total, they must be equal to 180 degrees. So in this side of the equation, we have in total alpha plus alpha, this is 2 alpha, beta plus beta is 2 beta, and it is equal to 180 degrees. If we divide this equation by 2, and find out that alpha plus beta equals to 180 degrees over 2, that is 90 degrees. That is to say, this is angle alpha plus beta, and it is a right angle. So angle MCB is a right angle. This is angle MCB, that is a right angle. You see, it is a right angle. AB, according to what is given as the equation, AB is a straight line. So if we focus on the left side of the straight line AB point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is a right angle plus this missing angle. In total they must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees in its size. Okay, so in the big side, this big circle, we have peripheral angle ACB that is equal to 90 degrees in size. Okay, and according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. And because of the fact that peripheral angle is CM is right angle, it must subset on the diameter of the circle. Peripheral angle is CM subset on AM, and therefore AM must be equal to, must be the diameter of the big circle according to rule 5. Okay. Chord AM is the diameter of the big circle according to rule 5. Okay. We know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. AM is the diameter of the big circle, therefore the center O must be located on AM. You can see here that indeed the center O that is it is located on AM, that is the diameter of this circle. So point O is the center of the circle, point M is the point of the circle itself. Therefore OM is the radius of this circle. We define the radius of this big circle as R. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copy the right triangle A and B in a new page, and we implement the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is triangle A and B, to the code from the original drawing. A and B equals to 15 units according to rule 10. AB in total equals to 9 plus 16, that is 25. And AM is the missing side. Again, the hypotenuse AB is 25. So according to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, but must be equal to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM. AM is the missing side, so limited it is, plus AB squared. AB is 15, therefore AB squared is 15 squared. So in total, we should find out that $625 equals to AM squared plus 225. Here we subtract 225 from this equation, and finally found out that 625 plus 225 is 400. So 400 equals to AM squared. Here we took out of this equation, and finally found out that AM equals to the square root of 400, that is 20. Okay, AM is the diameter of the big circle. Okay, here we already found out that AM is the diameter of the big circle. So the radius must be half of the diameter. The radius R must be half of the diameter. That is to say, the radius R of the big circle must be equal to the diameter AM over 2. The diameter AM is 20, therefore the radius must be equal to 20 over 2, that is 10. So in total we found out that the radius of this big circle R equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, the area of any circle must be equal to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is 10, therefore the radius squared is 10 squared. So in total, we can find out that the area of the big circle equals to pi times 10 squared. 10 squared is 100. So in total, we can find out that the area of the big circle equals to either 100 pi square units, or in terms of numbers, it is equal to 314.159 square units. We finished with the first question. In the next step, I presented to you the second question and solve the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So in the moment we have rectangle ABCD in this semicircle. We also know that line segment AM equals to 5 units in its length. And again, our mission is to find out the area of this rectangle ABCD. So first of all, we define all those four angles inside rectangle ABCD are right angles, and we define the center of this semicircle. This point is point O. We define the radius of this semicircle is x. So OA is the radius of the semicircle, that is x. In the next step, we join points O and E together by straight line. And OE is of course the radius of this semicircle, that is x. And because of the fact that the radius OE is on to point E, that is the point of tendency of tangent DC with this semicircle, and whenever radius is on to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, by doing this construction, we created here quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth missing rectangle, in total it must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing rectangle must be equal to 90 degrees in its side. So inside quadrilateral DEOA we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must be a rectangle plus a square. So we relate to this quadrilateral DEOA as a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DEOA side EO must be equal to the opposite side DA. But EO is x, it is the radius of the semicircle, that is x. Therefore DA must be also equal to x units in its line. In the next step, we join points O and M together by straight line. OM is the radius of this circle, that is x. We define this line segment OA as A, and we find this line segment MB as B. So in the next step, I copy the right triangle MOB in the page and implement it to what also on this right triangle triangle MB. So okay, this is the right triangle triangle MOB that I go from the original drawing. According to the Pythagoras theorem, this right triangle MOB, MO square equals to MB square plus BO square. MO is x, therefore MO square is x square, and it is equal to MB square. MB is B, therefore MB square is B square, plus BO square. BO is A, therefore BO square is A square. So in total, according to equation 1, we actually found out that x square equals to B square plus A square. In the next step, I copied the right triangle this right triangle A and B in the new page, and we implemented the Pythagoras theorem on this right triangle A and B. So here this is the right triangle A and B. This is the right triangle MBA, this is according to the original drawing. And according to the Pythagoras theorem, in this right triangle MBA, MA square, that is the square of the hypotenuse, must be equal to AB square plus BA square. MA is 5, therefore MA square is 5 squared, that is 25, and it is equal to MB square. MB is B, therefore MB square is B square, plus AB square. AB is x plus a, therefore AB square is x plus a square. So in total, we found out that 25 equals to B square plus x plus a square. So 25 equals to B square plus x plus a square. X plus a square equals to x square plus a square plus 2 times x times a. Here we have b square plus a square, so we can substitute b square plus a square by x square according to this equation, equation 1. We did it, and we found out that 25 equals to b square plus a square is x square plus x square again plus 2ax plus 2xa. So 25 equals to x square plus x square is 2x square plus 2xa. So in total, we found out that 25 equals to 2xa plus 25 equals to 2x squared plus 2xa. Here we divided this equation 2 by 2, and finally found out that 25 over 2 is 12.5, and it is equals to 2x squared over 2 is x squared, and 2xa over 2 is xa. So in total, we actually found out that 12.5 equals to xa plus x squared plus xa. Here we took x as a common factor of these two expressions, so inside the brackets we left only with x plus a. So in total, according to equation 2, we actually found out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. The area of an rectangle equals to the length of the rectangle times the width. The length of this rectangle ABCD is AB, and the width is DA. Okay, so it is the length is AB and the width is DA. AB equals to x plus a and DA equals to x. So in total, AB times DA is x plus a times x. And according to equation 1, x plus a times x is 12.5, therefore we can substitute x plus a times x by 12.5. And in total, we actually found out that the area of rectangle ABCD is equal to 12.5 square units. We finish with the first method. In the next step, I present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, we know that all the 4 angles inside rectangle ABCD are right angles. So those 4 angles are right angles. We define the center of this semicircle is O. We define the radius of this semicircle is x. In the first method, we already found out that dA equals to x, so not repeat on the same process. And in the next step, we define this point as n. We define this line segment OB as A. OA is the radius of this semicircle, that is x. So we join points N and M together with straight line. By doing this construction, we're going to do triangle NMA. And because of the fact that triangle NMA is subtend on AN, that is the diameter of the semicircle, and note that any triangle that subtend on the diameter of the circle must be equal to 90 degrees on its side. So this triangle NMA equals to 90 degrees because it's subtend on the diameter of the semicircle, that is AN. So this angle NMA equals to 90 degrees. In the next step, we define this angle as alpha. We focus on this triangle AMN. So in this triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, I copy it. But here in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. In the next step, I copy the right triangle A and B, the right triangle AMN in the image, and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles AMN and AMB to the point from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle A, that is a common angle that belongs to both triangles. So we can write down that angle A equals to itself. Angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I can prove that all the figures of this right triangle AMN are correspondingly equal to all the figures of this right triangle AMB. Therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AM of the right triangle AMN, side AM of the right triangle, this right triangle AMB, over side AN of this right triangle AMN equals to side AB of this right triangle AMB over side AM of this right triangle AMB. Over side AM of this right triangle AMN. Okay, AM over AM equals to AB over AM. AM is 5, AN is 2x, AB is x plus A, and AM is 5. So I don't know if we found out that 5 over 2x equals to x plus A times x plus A over 5. Here, because multiplied this equation and equation 1, if I found out that 5 times 5 is 25, so 25 equals to 2x times x plus A. Here we divided the equation and equation 1 by 2, and if I found out that 25 over 2 is 12.5, 2x over 2 is x, and total this expression equals to x times x plus A. So according to equation 1, we actually found out that x times x plus A equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Actually, we know that the area of an rectangle equals to the length of the rectangle times the width. And therefore, the area of our rectangle ABCD must be equal to the length. The length of this rectangle ABCD is AB times the width. The width is DA. And the length is AB and the width is DA. AB equals to x plus A and DA equals to x. Again, AB equals to x plus A and DA equals to x. So in total, we should find out that the area of rectangle ABCD equals to x plus A times x, but x plus A times x is 12.5. So we can substitute x plus a times x by 12.5, and we actually found out that the area of octagon ABCD is 12.5 square meters. So in both methods, we actually found out that the area of this octagon ABCD is equal to 12.5 square meters. Okay, thank you very much.